Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, no problems here. Today we're going to learn about momentum, but in a new twist here. It's called this: the law of conservation of momentum. Now, conservation, we learned about conservation of energy. Energy can't be created or destroyed. Guess what? With momentum, you can't create or destroy momentum. Or maybe it's not you're creating or destroying, but you can't lose. The total momentum of a system is equal to the total momentum of the system before and after. So it's like P initial equals P final. So there's some very interesting applications to this, and we're not going to go into too much details because ultimately it comes down to an interesting idea. But before we dive into this, let's talk about this. There's actually terms of, when we talk about momentum, there's two kinds of momentum. There's internal momentum and there's external. Okay. So for the bicycle, as we see right here, on the bicycle there are internal forces, the forces between the bicycle, she's holding on to the bicycle handlebars, so there's a force between her and her hands and the handlebar, and her handlebar and her. They're pushing back and forth. But those are internal forces, and we're not going to spend a lot of time on internal forces, but mostly on external forces. Because the internal forces don't have much effect on the problems that we solve. It does create interesting things. I was having a conversation with one of our students today, and we were talking about how things work, and he was saying, Mr. Bergmann, you know, when I'm lifting a weight, and I'm just holding a weight, I feel like I'm doing a lot of work. But see, that's internal because there's no motion. And those problems can be much more difficult. We're going to focus on the external features, and these are the ones that are conserved. And we're going to see things that are actually moving at a time. Stationary things and what happens inside of your muscles. It's quite a complex problem, and how energy is burned and holding something. There's actually motion happening between the contraction and the release of the muscle groups. So anyways, conservation of momentum, here is the big idea. The total momentum initial equals the total momentum at the end. Now this has direction because these are vectoral quantities, and that's going to play a key role. So when we talk about conservation of momentum, what we're really bringing up to, or we're leading to, is the concept of collisions. Okay, collisions and explosions. These are the two big ideas in conservation of momentum. Now, I'll talk a little bit about explosions in this video, and we're going to take two videos to talk about collisions, because collisions are a little bit more complex. The math can be a little bit crazier, but basically because momentum is conserved, we can make some interesting predictions about explosions and collisions. So let's do a demo. So what you can see, you may say, that doesn't feel like an explosion to me, but in an explosion what happens is you have an object which often has no momentum, P equals 0, and some objects get shot out of it. All right? But what does that do is it propels this object back in the other direction. And this is how a rocket works, guys. So if I've got a rocket, that's a rocket, okay? Trust me. Don't judge. Okay, in a rocket, it's filled with, chemicals, and the chemicals then shoot out particles at very high speed, and then, of course, what does that do? It pushes the rocket up. So when the rocket's sitting on the stand, or whatever it's called, the launching pad, then what happens is that it has no momentum. But if the P in this direction has to equal the P in the downward direction, if you expel things down, that's what causes the rocket to shoot up. Next up, let's look at some examples. So we got the two guys, and they're pushing two skateboarders at rest. The skate park, they're going to push them apart. So we got skateboarder number 1, and he has a mass of 45 kilograms, and he's going to be moving in this direction at 0.62 meters per second. We've got the second guy, right? They're going to be pushing off of each other at some point, and he's going to move at 0.89 meters per second. Since energy is conserved, what is the mass of this guy? Guys, you know what we get. This is super easy math. mv equals mv. The mass of guy 1 is 45. His velocity is 0.62. We don't know the mass of guy 2. he's going to go at 8.9 meters per second. Now we can talk about signs. You could say that's negative, but since they're equal and opposite, this is an implication of one of Newton's laws. We just divide both sides by 0.89 and we get m to be 31.3 kilograms. So this guy, if you think about it, that makes sense. He's moving faster. He's the lighter guy. The lighter guy should move faster because equal and opposite reaction, but this guy is moving slower because he's heavier. Make sense? So this is what we call an explosion, sort of a symmetrical-ish explosion. Let's do another example. So in this example, the kid's throwing is it a water balloon? He's throwing a water balloon, so we've got the guy, boom, and he's tossing a water balloon, and he's on a frictionless surface. The water balloon has a mass of 2 kilograms. He has a mass of 34 kilograms, and he throws this with a velocity of 14 meters per second. What would be his velocity after he throws it? Now, by the way, this is how astronauts move. If an astronaut wants to move out in space, they can just throw something. So if he's desperate, it's like, throw this, and that's going to push him back in the opposite direction. But anyways, it's a similar problem. It's like the last one. mv equals mv. So this is 34v is equal to 2 times 14. Divide both sides by 34, and his velocity is going to be 0.82 meters per second. Let's make sure that makes sense. He threw it at 14, and he's only going back, and actually we should probably say negative because he's going opposite direction. Negative 0.82, he's on a frictionless surface. Actually that makes sense because he is big, 34, and this is not so big, 14. Again, with a rocket, how would that work, right? You're going to send lots and lots and lots of small particles, but they're not going to be going at 14, they're going to be 1400. They're going to be like going really super duper fast, and then that's going to propel the rocket, in this case, up or down. So, conservation of momentum and explosions. Next up, we're going to learn about conservation of momentum and collisions. We'll talk then.